My name is Kitty Wang, and I'll be covering my falling slinky lab. The purpose of this lab is to analyze the position of the bottom of a slinky falling from rest. We will also determine the effects of gravity and drag on the motion of the slinky. At the end of the lab, I could create a graph comparing the predicted and observed motion of the bottom of the slinky in the y direction. So one principle we use is Newton's second law, which includes the momentum principle, which can be used to derive the velocity and position update formulas. We use Newton's second law here because we need to find the net force acting on an object by summing its forces from interactions with other objects. On the slide, I've listed out the equations I use for the gravity, tension, and drag forces, and the velocity and position update formulas. For the force of gravity, I made j hat point up to signal the positive y-axis, so our slinky falls in the negative y direction. Note that the net force of the slinky's force and the gravitational force is 0 when the slinky is at rest or it's in static equilibrium, and thus the magnitude of the slinky's force and the gravitational force are equal. I used a video already recorded from YouTube, so I made my system the slinky and the surroundings the Earth. For the initial conditions, I have them all listed out on the slide. I estimated the initial stretch length by comparing its height to the height of the man. You can also see how I set up the coordinate system in Tracker and the graph of the data collected in Tracker, where I have the slinky falling in the negative y direction. For the computational model, I plugged in the initial conditions I mentioned in the previous slide and used Newton's second law to find F net equals the sum of the force of gravity and the tension force of the slinky when the slinky is in static equilibrium, and F net equals the force of gravity and the force of drag when the slinky is falling. Then, using the velocity update formula in both time steps, I calculate the object's new velocity and use that to calculate the slinky's new position in the position update formula. Then I printed out the time and y position of the slinky to use that data on the graph of the results in the next slide. So here's the data from the computational model and the observed data on one graph. Notice how for the position graphs, the experiment roughly models the computational model. However, if we look closely, we will notice that as the experiment goes on for a longer amount of time, it deviates more from the computational model. So this could be because of human error when locating the center of mass of the object in Tracker because the video quality is not great. It could also be because the drag force value could have been better tuned in the computational model. And another reason could be that we have some other unaccounted force in the real world affecting the slinky. For our what does it mean question, we can see that the bottom of the slinky remains at a constant y position until the top of the slinky reaches the bottom of the slinky. You can easily observe this by looking at the graph from the previous slide. About the first 5.8 seconds, you can easily observe this. And also note that the constant position is because net force equals 0, since the magnitude of the force of gravity is equal to the magnitude of the force of tension. So to conclude, we used Newton's second law to analyze the position of the bottom of a slinky falling from rest. We determined the effects of gravity and drag on the motion of the slinky, and we noticed that in the real world, there may be unaccounted forces affecting the system.